Good afternoon, everyone. It's my privilege to warmly welcome Dr. E. Prasad, Professor and Head, Department of Physics, Central University of Kerala, for today's session. We are delighted to have you, sir, for this session. Please.
Thank you. I'm audible, right?
Yes.
Yeah. So shall I start the session?
Yes, sir, you can.
All right, thank you. So, warm good afternoon to one and all. Myself, Prasad, currently working as head of the department and professor in Department of Physics, Central University of Kerala. So by training and by profession, I'm a physicist. I work in nuclear physics. I did my PhD in nuclear physics accelerator-based experiments at Inter-University Accelerator Center. Some of you might have heard about that. It is one of the accelerator facilities we have under the Department of Atomic Energy and University Grants Commission. I did my master's from Calicut University campus and then a PhD from Nuclear Science Center Delhi. And a few years I was in Australian National University as a scientist, and also a few projects with bilateral projects with Russia and other countries. So it's my pleasure to talk to you, and I express my sincere thanks to one of the organizers, Dr. Praveen, and other faculty members from Sripati. And in fact, this is probably the second time I am addressing faculty or students from engineering background. And first time I addressed was long back, maybe around 10 or 12 years back. And Dr. Praveen asked me to talk about physics, applied physics and technologies. So I was also confused in the beginning what to talk about, whether I can confine my talk to nuclear technologies or accelerator physics. And then since I was not very sure about the background of the participants, I thought I'll try to give an overview how and where physics is playing a vital role in engineering technology. So most of these slides, I mean, the information, whatever I'll be sharing might be known to you. So it's a sort of overview. Towards the end, I'll be talking something about a few emerging technologies and what are the engineering challenges and role in that. So, of course, this slide, I was not having sufficient time. I grabbed it from the internet. I thought it conveys something. So, when you ask, I mean, most of you would be encountering in the first semester physics students in engineering colleges, they are coming after +2. And if you ask or if you try to define what physics is, I thought I'll start from there. Physics is a fundamental science which tries
Maybe
to.
please from outside. ये इंडिया की बाहर से है मेरी
Sorry. So, which is trying to understand how nature works and is try to understand the fundamental laws of energy, matter, and space and time. So, +2 definition or maybe 10th class definition. And if you try to find the origin of physics or science, it dates back to ancient civilizations where probably philosophers try to understand the natural phenomena by observations and measurements. People. Is it a communication to me, or otherwise, please mute your mics? So in the early stages itself, people were very much fascinated by the movement of stars and moon and other celestial objects. And they realized that the climates and other things changes and they could plan their cultivation and other activities. And these observations and say measurements, actually became a sort of quantitative one. Probably due to the pioneering contributions of Galileo Galilei, who introduced novel measurement techniques, and then obviously by Isaac Newton, who introduced the laws of motion and laws of gravity. These are all known to us, and in fact, that led to the foundation of physics, or rather, the classical physics or classical mechanics, and later on in classical physics, we know we have thermodynamics, we have electromagnetism, optics, and in modern physics, you have quantum mechanics. So by 20th century, relativity came into picture, quantum mechanics came into picture, and we expanded our understanding beyond the limits or realm of classical physics. And for the engineers, I would say physics is an instruction manual, actually. Basically, an instruction manual for reality. And they design bridges, they design spacecraft, they design communication systems, they design and physics. Probably I'm muted. Am I audible? Hello.
yes
All right. Okay. So yeah, that's what physics actually. So today, physics is remaining at the heart of all scientific discovery, technological innovation, and it drives electronics, it drives semiconductor industry, it drives AI, and I think there is a special session on artificial intelligence as a part of this FDP, and it drives quantum communication and all. So Just a brief classification, as you all know, and then just I thought of starting the talk about a few news from space science. Probably people call it as rocket science or hi-fi technology. And we know that in 2023, August 23, India landed on the south pole of moon. Our Chandrayaan mission, Chandrayaan 3, successfully landed on the south pole of moon. And August 23, we are celebrating as National Space Day. And that is, I mean, we are all proud of that. And India is the fourth country which could actually land on the surface of moon, and the first country which could land on the south pole of moon. And it has its own significance and relevances. And again, we recently heard that, we were happy that Sunita Williams could come back. She went for a week or a few days to International Space Station, and she had to stay there for about 286 days due to some technical issue in docking the the spacecraft. And India, ISRO is also planning to have our own in a space station, the Bharatiya Antariksha Station, which is planned to be between 400 to 450 kilometers from the surface of Earth, and which can accommodate 3 to 4 astronauts. And by 2028, we are set to launch our first module, and by 2025 we'll be completing this, and we'll be having a full-fledged Bharat BAS 1 by the Antariksha Station will be commissioned. And again, another very proud moment is that India has launched our solar mission, Aditya L1, which is actually now looking at the sun with a closer look, and it's Corona. L1 is one of the Lagrange, if you had gone through the news. It is, the basic classical physics. It is one of the Lagrange points, which is the stable configuration where the gravity of sun and Earth basically balances the motion of our spaceship. It has its own advantages. We can see sun without any mass. Our Earth will not be coming in between, and that is the point. One of the points where the space station requires minimum energy to power the plant. And again, NASA is aiming to send man to the Mars by 2030, so crewed man mission to uncover the red planet secrets. So as I titled it, it all sounds very hi-fi, sci-fi technology, and but eventually, to a great extent, this is basically classical physics. So for the rocket launching or spacecraft launching or lunar mission or solar mission or crewed mission to Mars, basically, to a great extent, it is Newton's laws of motion. It is your Kepler's laws of gravity, and thermodynamics and fluid dynamics playing a great role. So engineers also who are working in this area must be really fond of this classical physics, in that sense that they could get answers to questions like how much fuel is required for a given rocket, or what could be the thrust for a given spacecraft, or which orbit I have to choose for having a stable trajectory, what would be the effect of gravity of nearby objects on this spacecraft or satellites. So classical mechanics is at work in space physics, except the technology, except the kind of materials that we use, and except the sort of communication that we follow. Otherwise, classical physics is basically ruling the space missions. And I mentioned that in space physics, we have thermodynamics. which actually decides the thrust and the energy and the fuel efficiency. And thermodynamics otherwise also appears in our plays a vital role in our day-to-day activities in air conditioners, in refrigerators, in car engines, and probably engineers must be, we have a set of thermodynamics laws, and for engineering students or those who are working in this area, they will be really fond of second law of thermodynamics, which is nothing but the Carnot cycle and Carnot engine, which gives you a measure of how much or what could be the maximum efficiency one could attain in reality. You know that Carnot cycle is Carnot engine and Carnot cycles basically and a very idealized engine, and to have 100% efficiency, that is what we actually look for. Basically the engineers, is possible only according to the second law of thermodynamics, possible only if the low temperature reservoir is at absolute zero. T0 is equal to 0 Kelvin, which is impossible. So we have Otto cycle in the case of petrol engines, and then diesel cycle, and in the case of gasoline turbine we have Brayton cycle and all. So thermodynamics is also coming in engineering aspects a lot, and again the classical physics is playing a significant role in this. And another area, electromagnetism. Richard Feynman once said, maybe if historians look back 1,000 years after, thousands of years from now, they would definitely appreciate and remark that the Maxwell's equations is one of the greatest achievements of humankind or scientific community in the 19th century. These four equations, I have shown where it actually operates in mobile phone, where it is actually useful. Mobile phone, radio and TV communication, Wi-Fi, GPS, radar system, radio astronomy, laser, NMR, a few, to name a few. And it is everywhere: electric power generation, telecommunication, electronics, inside the chips, AI and computing, wireless networks, medical imaging, sensors, etc. No, and this is one slide I just made using Google Gemini. I think you might see somewhere, which basically gives you a very interesting feature. I mean, it has everything, starting from the very basic application of electromagnetism to most modern application. And another area which I felt I would mention as electronics or semiconductors. And our government is pumping a lot of money on semiconductor industry in the last few years. So if I am asked to name a few technologies which are very crucial, which will be booming like anything in the next few years, 5-10 years, one will be the quantum technology, one will be, of course, biotechnology and nanotechnology, and the semiconductor industry is also booming like anything. And we are, the government of India is providing a lot of fund to semiconductors after COVID, because for the semiconductor chips and all, we have been depending upon other countries, and after COVID, all the supply chains were very much disturbed, and we realized that we have to have our own production mechanism. And with that in mind, government of India is putting a lot of effort in establishing semiconductor industry and semiconductor technology in-house. And in fact, my university, in Central University of Kerala, also we are starting a course on BSc 4-year program, honors program in semiconductor physics, not technology, semiconductor physics, which will be, and we have a number of scientists who are working in semiconductors and nanotechnology, and we believe that we'll be able to contribute significantly to this. So the history of electronics is one of the most transformative journeys in human civilization. One would admit that. And semiconductor physics is the foundational science enabling the digital age, what we are enjoying today. And it started with vacuum tubes. You know that vacuum tubes were operational in 1940s, and they were very bulky, highly less reliable, and power hungry. And soon, the semiconductor age was actually launched by the discovery of transistors in 1950s. And further, there were developments to IC integrated chip, and you could see here the first integrated chip. And then today we have hundreds of millions of chips or millions of transistors integrated in our computers and all. And again, from a very bulk size to we are talking about millions of transistors in a single chip. So the size miniaturization happened, and that led to a lot of developments in digital age. But at the same time, there is a natural limit, one should admit. So when you reduce the size, that is what we are seeing currently in our digital electronic equipments. When you reduce the size, there is a natural limit. So in general, so if you consider a transistor, you have the source, drain, and gate, and you can improve the electrical performance by reducing the gate length. But when the size becomes a tens of nanometer, like 20 nanometers or 30 nanometers, the electrical performance suffer a lot. It gets deteriorated. There are many reasons. Those who are working in electronics or lead areas may be knowing that. And one fundamental reason, as a physicist, I would say, is the quantum tunneling phenomena. So this tunneling phenomenon actually leads to sort of current leakage current, and that is very detrimental in the case of semiconductors. I mean, in the case of these transistors, size miniaturization has a limit, a natural limit, which is basically originating from the fundamental quantum principles. And we can do away with all other issues technically, but this fundamental problem one cannot bypass. So of course, then you have to go for other materials, and one is fin FET. Instead of planar FET, today's electronics go for fin FET. So we have a design where you can see that there is the fin-like structure, the conducting gate. The gate is actually surrounded by a channel which is protruding from the silicon surface, and that has got a fin like structure, and that improves the performance. And fin FET is very much in use, and further a lot of works are actually happening basically in nanotechnology to identify new materials. And one of the promising development is gate all around sort of transistors, where we are using the channel from nanomaterials or nanowires or nanosheets, and these are also coming extensively in the coming years, and the future is probably in that direction. A future is very bright, but there are experimental challenges. There are technological challenges where one could really have innovative ideas and new technologies, particularly a challenge for the engineering students. And I was mentioning about the early era of electronics, and all of you must have heard about this ENIAC, electronic numerical integrator and computer, which is just to show how big and how bulky the electronic system was in 1940s and 50s. I just thought of showing this. You are all probably familiar with this. So ENIAC is world's first programmable electronic general purpose digital computer developed during Second World War, and it has something like 30 tons of weight, and it was one single computer was occupying about 1,800 square feet of space, approximately 17,500 vacuum tubes, and 7,200 crystal diodes, and you can see the speed. It was capable of 5,000 editions per second, and I was mentioning that these technology based on vacuum tubes in the early days. When I was a kid, I have seen some radios which were using these sort of vacuum tubes and all. The power consumption, they were all very power hungry, and the power consumption was something like 150 kilowatts of electricity to run this single computer. And today we know how much power is basically required for running a normal computer. And from there, we are now in quantum era. We are talking about supercomputers. We are talking about quantum computing, and we are talking about machine learning and other. So that is the status. That is the sort of technological development and technological challenges, thanks to the developments in electronics and semiconductor area, semiconductor physics. So starting from fundamental classical physics to the current scenario, the quantum computing era of quantum computing and quantum technology. As I mentioned, physics, the subject, though it's a fundamental subject, it is in the driving seat as the architecture of reality and innovation. So I mentioned that there are a few technology which are very vital in deciding even the GDP of the countries, and one such technology is quantum technology. So I mentioned about how physics, or the discipline of science and subsequently physics originated, and it became classical physics. And at some point, and this classical physics, the same Newton's equations, same Kepler's law, and same Carnot engine or thermodynamic principles, Maxwell's equations, they were all exceptionally good in explaining the fundamental phenomena, all the phenomena that are happening around us. And you see that it can be used in space technology. It is used in lunar mission, solar mission. You decide at what point you are sending your satellite, and at what point it will be landing. And you must know that all these bodies are not stationary; they are moving around another object because of gravity. And the powerfulness of these equations are so solid that you can fix the target and you can achieve, you can reach that target. But the same physics was observed to be miserably failing when you try to understand the micro world. So by till 19th century, you know that physics was the boss. Classical physics was the boss. And then powerful accelerators and other equipments came into picture. And then we could look into more deeper inside atom and subatomic particles. And then it was realized that the language that we are using to explain these fundamental aspects, and the language that we are using in technology related to that is really getting shattered. The classical reality is shattered when you go to micro world, and the language and the way it behaves sounds so weird that classical physics or classical physics has no answers. And so a new formalism, radically different from the classical formalism, has been developed. And Richard Feynman once said that nature itself is not classical. Though it sounds so classical to us who we are a macroscopic being, if you want to make a simulation of nature, or if you want to try understand nature, try to understand the phenomenon, you better make it quantum mechanical. And it's a wonderful problem because it doesn't look so AC. That's what Richard Feynman once said about how it works, how things work in nature. And in 1920s, I just thought of, since we are talking about quantum technology and quantum 2.0, I thought when I went through the syllabus, I saw that the students are going through quantum mechanics as well. So I thought probably I'll talk, I spend 1 or 2 slides on the quantum 1.0, and then we will try to say something about quantum technology, or something about quantum measurements and all. So in classical physics, if I want to represent, say, an object, I can talk about its position. I can talk about what is the velocity of that, and that characterizes the position and velocity. And if I throw that, if it is a stone, if I throw it somewhere, I can say where it will land, with what velocity it will land, and when it will land, provided initial conditions are known. It is so probabilistic, it is so deterministic that if I send say satellite from Earth to Moon, it will go there, it will follow my instructions, and it will go there and it will reach there. But when you go to microscopic world, it is not at all classical, it is not at all deterministic, it is completely probabilistic. You cannot represent a particle by the classical senses like position or momentum or velocity. Instead, in classical physics, quantum physics, you talk in terms of something called wave function, the probability amplitude. And it's a complex quantity, as you all know, and it doesn't have any meaning. And the one quality, first of all, we introduce is the probability density, the mode square of this thing, which has a meaning of finding an object probably at some positions, at some coordinates. And then there is no position observables. There is no position or momentum, just like classical physics says. Instead, you have operators. For position, there is an operator. Momentum, there is an operator. Energy, there is an operator. And when they operate on your wave function, the state function, that gives you something. And that is what you are supposed to get, or you will be getting when you make a measurement. So a measurement actually bridges reality and the so-called wave function in that case. So operators, they are also following certain rules. And of course, again, another thing is that there is sort of uncertain principle known as uncertainty principle. You cannot arbitrarily talk about measuring something to objects simultaneously with arbitrary precision. They are all related through some relation which is called uncertainty relation. Position and momentum, canonically conjugate variables, cannot be measured. And another very astonishing consequences or say aspect of quantum mechanics is quantum mechanical tunneling. If you are placed on the other side of a wall, classically you can, and if you have the height of the wall is too much, you cannot come on the other side. But quantum mechanically, there is something called tunneling probability, and that is how alpha particle comes off the nucleus, and many radioactive decay happens, and that is how things work in the micro world. And instead of your loss of motion, you have the Schrodinger equation, which gives the dynamics, which says how the system evolves, how quantum system, I would say, evolves as a function of time. So these are all prerequisite, and these developments happened in the 1920s and 30s, and we today call this as first quantum revolution, quantum 1.0. So in quantum 1.0, in the first quantum revolution, we try to formulate and we try to understand quantum systems, and we try to explain quantum systems and understand natural phenomena that are actually happening in the micro world. And two important aspects which are not possible in classical regime, the weird nature of quantum, in some sense, quantum physics, is the quantum superposition and measurement problem. So in classical physics, in classical sense, if I have a coin, I can have either head or tail. There are two states, head or tail, and the classical system exists in multiple states, different states with different probability at a given time. But quantum system can have a superposition of the states. All of you must have heard about this Schrodinger cat and other things, such experiments. So physical system, quantum mechanical systems can simultaneously exist in different configurations and or locations. And this is a powerful aspect of quantum mechanics or quantum systems, and that is what is being used in quantum computing today. I'll come to that later. We use something called a Hadamard gate to create this quantum superposition. And but when suppose you have so if I take the example of this Schrodinger cat, you can have classically you can have either a living cat or a dead cat, but quantum mechanically, I mean, it cannot be directly related to a macroscopic thing like a cat, but quantum mechanically, both possibilities are possible and with equal probability. And but when you make a measurement, so when you make a measurement actually kills that system, and the wave function, which was previously existing in multiple states, now collapses to one observable. And this is one of the phenomenon that even in physics we could not give a very say acceptable explanation. How measurement is actually taking a quantum system which is highly mathematical to reality. And when such a thing happens, when measurement happens, how the system collapses into one of the states. So when you have the Schrodinger cat experiment, till you open the box or till you open the box, you have the possibility of cat living as well as dead. But when you open the box, you would either see a living cat or a dead cat. So this so you would only see one possibility. Just like when you toss a coin, you have either heads or tail as a possibility. So there are multiple explanations, and one of the explanations for this measurement problem is quantum decoherence, which is more or less widely accepted. So I was mentioning about quantum mission and quantum technology. So in 1920s, in the beginning of 20th century, we realized that quantum classical physics cannot explain the microscopic world. You need a different formalism, a radically different, a completely different formalism. You cannot wear classical shoes and try to explain quantum objects. It is completely different, and you will land in trouble when you try to explain it in classical norms. Of course, a lot of developments have happened over the years, over a century, and today we are in a position to actually manipulate these quantum systems and manipulate in such a way that you can use these quantum states and quantum aspects and properties of quantum systems for various applications. And that is where the role of engineers and role of innovators are actually coming into picture. And recently, Government of India, I think it was in 2023-24 budget, Government of India allocated about 6,000 crores of money for the quantum mission, national quantum mission, to develop and support quantum technology. So the mission is basically to develop magnetometers to support and design and the synthesis of quantum materials such as superconductors. You will see later on when I talk about accelerators, where superconductors are highly useful, novel semiconductors, and other topological insulators and topological materials for the quantum devices. And so in that way, many institutions and research organizations are funded like anything to promote or to have quantum technologies built in-house. And four verticals in that National Quantum Mission: the quantum computing, quantum communication, and communication quantum key distribution using QKD. One could use, quantum technologies could be used, and then sensing and metrology and quantum materials and devices. So from observing quantum mechanical aspects and trying to explain what it is, what is actually governing fundamentally in their behavior, probably weird or normal, we are in a position to actively manipulate these individual systems and can be used for various purposes, which are superior to the techniques that we were otherwise using classical physics or classical techniques. And again, that is what I mentioned. There is a shift from pure physics domain to applied physics, or and the consequences are quite very high. These quantum technologies could be used for national security, national sovereignty, and the entire GDP in the coming years will be dramatically influenced by the quantum technology. It is projected that I got it from somewhere. It is projected that quantum technology is going to unlock between $1 trillion to $2 trillion by 2035, which will be significantly altering global GDP share among the nations. And we cannot be a silent spectator. And that is why government has taken a proactive step to support quantum technology and quantum mission and quantum developments, engineering, and innovation in quantum technology. So in classical computer, for example, in quantum computation and classical computation, you know that in the case of classical computer, we have two digits, binary digits 0 and 1. And we store the information in that. And you have the logic gates and circuit chips. And for example, if I want to convert say bat into binary number, you know how to do that. Very simple, say +2 physics or maybe 10th class physics. And this is how it looks like in ASCII format, decimal format, and the binary format. And that is how actually information is being stored and processed in classical computers. And all our computers, supercomputers, servers, calculator, etc., store information in classical bit. And we have very powerful supercomputers as well. But they are all based on this. Being a nuclear physicist, we used to do a lot of experiments and a lot of theory. So, you know, nucleus is a quantum mechanical object. If you look at atoms and crystals, you have infinite number of crystal is actually defined in that way. So atomic physicists are relatively in a better position to explain things that they observe. But for nuclear physicists like us, for example, if I say oxygen 18 or oxygen 16, which has got 8 protons and 8 neutrons, it is only having 8 protons and 8 neutrons. So your statistical physics or statistical mechanics or those kind of techniques cannot be applied to your nucleus, because those techniques will be giving you a very good answer. I mean, the proper answer when n tends to infinity. But I have only 16 particles. And unfortunately, the 16 particle, oxygen 16, has got 8 protons, 8 neutrons. These 8 protons and 8 neutrons are unfortunately quantum particles. They are quantum objects and they behave quantum mechanically. So I cannot use classical physics to solve how they interact and understand what is happening. And I need to use quantum mechanics. And then there is a problem. You can use, I have showed you the Schrodinger equation, H psi is equal to E psi. I can solve it. If I have two bodies, this H has the kinetic energy and potential energy, the Hamiltonian. When you have two bodies, then you have individual kinetic energy, potential energy, and an interaction term. So generally, we break that two-body problem into two one-body problem. It is mathematically easier to solve. When it becomes three-body, then first body will interact with the second one, second body will interact with the third one, second body will interact with, first body will interact with the third one. So there will be a lot of interaction terms. Then it becomes highly difficult to analytically solve it. You have to use computers. You have to use so-called, I don't know whether you are familiar with that, Hartree-Fock calculations and time-dependent Hartree-Fock calculations. For one system, one initial conditions, if I want to run quantum mechanical calculation in supercomputer also, sometimes it takes months and years. So, forget about normal computer. These kind of computation that what we are using, your classical bits and classical computers, even though you call it as supercomputers, they require months of calculational time and infrastructure. You know how expensive running supercomputer is. In the institute where I did my PhD and I'm doing my research, there is one supercomputer, Rudra, and recently I was told, I was shocked to know that the entire setup cost around 10 crore, but annual monthly current bill, electricity bill is around 1 crore or something like that for maintaining that. So just think about running a quantum simulation in a nuclear physics problem to understand it, which may be used for developing a reactor technology or a fusion reactor technology. I really want to know how things work, how this interaction happens. And that would be probably very helpful for me to design a nuclear reactor material, which is very, very essential in nuclear power generation. Just imagine I'm spending say 1 month or 2 months in the supercomputer. So you can just imagine the time waste as well as the resources. That's how quantum systems behave, and that complicated the kind of calculations are to get proper results. In classical computer, we use classical bits, and in quantum computers, the so-called quantum computers, we have the so-called quantum bit. All of you probably know it's called qubit. It's a basic unit, just like our normal qubit. And so it can be, so a classical bit can be either 1 or 0. But here we are using the powerful principle of quantum mechanics, the superposition of the states. And so a qubit is basically a superposition of these two states. And generally, in quantum computation, the first gate that is used is to create a superposition from one of the states, which is one of the gate is Hadamard gate. So if you have, say, n qubits, and this quantum system can simultaneously occupy that superpose in all the states possible. That is what the superposition principle says. I mentioned a couple of slides before. So if you have n qubits, there will be 2 to the power n classical bits required for doing that sort of a calculation. And so that problem becomes, doing quantum computation in classical computers, be it a supercomputer as well, is almost impossible, because if you have 3 qubits, equivalent classical bit requirement is 8, 10 becomes 1024. And if you have, say, 300 qubits, you see the number 2037035976 into 10 to the power 90. This many equivalent classical bits are required for performing that kind of a calculation. And as I mentioned, in qubit, it's a superposed state quantum building blocks of quantum computer. It's a two-state system, and so you have the 0 state and state 1, just like the head and tail of a coin. So when you toss a coin, and when the coin lands on your hand, you know it is either a 0 or 1. But when it is in the air tossing, it could be, it's like a sphere. It can have all the possibilities. And generally, this quantum qubit can be written as a superposition of these two states, alpha 0 and beta times 1. These are the so-called Ket states. Quantum states can be represented in that fashion, in a funny way, putting them between these symbols, one vertical line and the other one, probably you must be knowing. So the poles basically represent those states, pure states. 0 is the North Pole and 1 is the South Pole. But as I mentioned, the quantum state can be anywhere. It can be a superposition. So any point on this sphere represents a qubit, and the two poles, North Pole and South Pole, represent the state 0 and 1. And this way of visualizing, because I mentioned that the state is like alpha times 0 plus beta times 1, where this alpha and beta are basically complex amplitudes, and we have a problem in realizing or visualizing complex amplitude. And so this is the way generally this bits are shown. This is called a block sphere. So it's a geometrical representation of a qubit and qubit. So, so far I was just mentioning about something so, say, random or arbitrary stuff. So can we have such states, two states in reality? That is another question. I can talk about any random stuff which is highly hypothetical and say that using this, I can do this and that. But if there is no realistic thing I can utilize, then it's wastage of time. But in reality, fortunately, there are many two-state systems available to us, which will be used for quantum communication and other quantum technology. And one is electron. You know that electron is a fundamental particle, part of the atom. In 10th standard, you study the fundamental structure of atom, and nucleus is at the center, electrons are going around it. And this electron is a fermion, which has got a spin half, and it has got two orientations, one spin up state and one spin down state. So these two states, if I could utilize as say equivalent to your 0 state and 1 state, and till you measure the spin of the electron, it's a quantum mechanical object. It's a quantum system. So the state of the electron will be in a superposition of the spin up state and spin down state. Only when you make a measurement, the state collapses to one of the possible state, either spin up or spin down. So qubits can be in reality for us can be realized in terms of this electron spins, number one, and there are many other cases. And another is photon, electromagnetic radiation. The polarization, the direction of photon also could be utilized for having these states, qubits, realized in reality. So the polarization of photon also can be exploited to have our goals in reality. And I mentioned earlier about occupying, quantum systems having superposed state. And another very interesting phenomena that is observed in quantum physics is quantum entanglement. So particles of same origin, which were once connected, always stay connected. So as I mentioned, if I have two photons, And if I send one of the photon to say California or New York, and I retain the other photon, if they are entangled system, if I disturb the photon with me, if something happens to the photon which is available with me, and its state changes, the same thing would happen to the partner which is in California or New York. That is what it is in simple sense entanglement means. So particles of same origin which were once connected always stay connected. Whatever happens to one partner will be instantaneously communicated to the other one. So this aspect is highly used in quantum communication in particular. So even if they are separated and move far apart in time and space, they continue to share something beyond mere bond. Their original quantum states, they shed their original quantum states and take a new one. United quantum state they maintain forever. So local measurements on faraway particles can exhibit strange correlations, almost as if one particle can instantaneously influence the other one. And this feature, the so-called quantum entanglement, is the heart of quantum mechanics, and it is the heart of quantum technologies and quantum quantum communication. So two basic cornerstones in quantum technology, which is coming from pure quantum mechanics. The first one is obviously the entanglement, as I mentioned, which allows the combined state of qubit to contain more information than the classical one. And the second thing is principle of interference. When quantum systems can constructively interfere or destructively, they can have constructive as well as destructive interference. And this principle of interference basically allows you can tune it in such a way that you can amplify required signals or required information, and you can reduce, cancel unwanted solutions, and that's how you can enhance the correctness of the solution as well. So these two fundamental principles are the cornerstones in quantum 2.0 in quantum technology today. And just a slide how it works. And today, quantum technology, people are trying to use it in quantum communication as well. So they could send from Alice, one could send a photon to Bob, the receiver. And even if someone, the beauty is that even if someone tries to understand or tries to, and if actually tries to understand what is being transferred from A to B or Alice to Bob, that measurement actually alters the quantum system. Number one, measurement kills the quantum superposition, and this is actually detectable in the case of quantum system. So if Alice sends some information to Bo, and it is very much possible for Bob and Alice to know that someone is sitting in between and listening to them. And because the person who is actually sitting in between doesn't know the actual quantum state, and the act of measurement will leave some traces which the sender and receiver can easily understand. And another thing is that no cloning theorem or no cloning principle, that a quantum system cannot be easily cloned just like classical system. And this is, I just asked Gemini to create some future quantum internet, just an image created using Gemini only. Probably you could see the symbol of Gemini also somewhere. And but it is not a joke actually. China has recently sent a quantum satellite, it's MESSIAS or something like that, if I remember it correctly. So in the coming years, quantum communication and quantum internet, we will be witnessing quantum internet and quantum communication pretty soon. And just to give some more basic idea, so in classical computers, we use this AND gates and XOR gate. OR gate, fundamental gates. But in the case of quantum computing, as I mentioned, you have to have a superposed state. You have to have a superposition of the states. It's a starting point in most of the cases, and that is what is done using Hadamard gate. I mentioned it a couple of times earlier for some reasons. So this is the representation. This is h as 1 by root 2 and 1 minus 1. Quantum mechanics has different, there are different formalisms. One is the Schrodinger formalism, where we write partial differential equations, or the entire formalism is actually solving the Schrodinger equation, which is nothing but a differential equation. And Heisenberg actually introduced the matrix mechanics. So this is H is basically a matrix representation of this Hadamard gate, and the factors are always sitting outside. If you see in the case of wave function, etc., they are the amplitudes which gives the probability, or they are generally the normalization constant. So in the case of Hadamard gate, you could represent it this way. So if you have, say, a spin down state, as I have shown here, if you have a spin down state, and if you give that spin down state to a Hadamard gate, you will get a superposition state which has both spin down and spin up. So it's shown here mathematically. So when H operates on 0 state, you will get 1 by root 2 times 0 state plus state 1. So initially you had only one state, and the Hadamard gate, when it operates on it, it creates a state 0 as well as 1. Similarly, when Hadamard gate operates on one state, so you can assume that 0 is your head and 1 is your tail. Then Hadamard gate operate on the tail state. It would again produce a superposition of head state and tail state, but with a relatively negative sign in between. And you could state other states as well by the application of this Hadamard gate. So this is one of the very important logic gates used in quantum computing. You must be familiar with Shor's algorithm and many other algorithms. Shor's algorithm is used for factorization, very famous one, a factorization of very big numbers. And this Hadamard gate is used in that. And normally for creating entanglement, we use this Hadamard gate and C0 gate. So a qubit initially in state 0 becomes equal superposition of 0 state and first state, state 1. And a qubit initially in one state becomes a superposition of 0 and 1 with a relatively. So physically, if 0 is spin up state and 1 is spin down state, after Hadamard gate, we'll get 1 by root 2 times 0 state plus 1 state. And so I just mentioned that this is in the developing stage. We know that the quantum technologies, we can manipulate, that is the right word one should use, manipulate the quantum systems in the right way. And if we could do that by invoking fundamental quantum principles, basically based on the superposition, which once we saw with a sort of, confusion and quantum entanglement, which probably didn't make sense to those who think it in a classical fashion. We could use these principles to exploit or manipulate quantum systems. And it's, as I mentioned, it can be used for cryptography, it can be used for communication, navigation without GPS, and many other applications, even in financial sector, financial modeling. And by 2030 or 2035, the entire economy will be quantum economy. But obviously, it's not a cakewalk. Development of quantum technology is not just a physics problem. It's a real challenge is in your court, those who are working in engineering area, scalable, and first of all, you have to have quantum systems scalable and manufacturable quantum systems. And a lot of research is actually happening in universities and institutes also in R&D level to have these quantum materials synthesized in the laboratory. So there are challenges, endless challenges, and endless opportunities in quantum technology. So that is one thing I thought I would just mention, since you are teaching physics students and you have a paper on um, quantum mechanics, and you'll be introducing quantum mechanics to the students. Probably it would be nice to talk about quantum technologies and related stuff and how they will be getting benefited. And there are a lot of simulations. I have some simulations, screenshots of simulations at the end of this talk. So there are a lot of websites where they could try learning quantum algorithm, and it gives kit and other things. So please encourage your students to fetch these at least free platforms where there are quantum simulations to understand quantum physics in the first place, and to manipulate and play with quantum computing algorithms and creating algorithms. Another area I thought I may talk a little about is sustainable. What is the time? Sustainable energy technology. And so you know that meeting global energy demands while reducing carbon emission is one of the greatest engineering challenges in 21st century. We, India, depend a lot on fossil fuels for energy production. And the consequences you and me, all of us, are experiencing nowadays in terms of petrol and fossil fuel hikes, and even in our kitchen and hotels, we are actually experiencing how the geopolitical equations are actually changing this energy dependency. So unless and until we become self-reliant in technologies, self-reliant on energy technologies, and that too sustainable energy technologies, probably the future may not be that bright. It will be definitely dark, considering the volatile geopolitical equations. Earlier, we had Ukraine, Russia were creating a lot of issues, and now in the Strait of Hormuz, again we are facing a lot of problems, and that is reflecting even in our kitchen nowadays. So forget about all other developments, whatever we are going to have. India will be becoming a developed country by 2047, and we will be requiring more and more energy. Forget all about that. Today, we know that all this dependency on fuels, especially fossil fuels, is even affecting our kitchen. So we are also feeling the heat of it. So that is one concern. And second thing is so becoming energy, self-reliance in energy technology is one thing. And we have a commitment to our coming generations in terms of carbon emission and resources depletion. So, so obviously, the current goal, one of the sustainable goals, is to have sustainable energy resources, because we have a global requirement is rising up like anything. I have taken this from some article where it is shown that from 1990 till 2040, 2050, what will be the sort of energy, total energy consumption and total energy requirement. And you can see that for developing countries like India and China, it is exponentially shooting up. And at the same time, if you are depending on fossil fuels, you know that it is leading to a lot of issues in terms of carbon emission, global climate change, temperature rise, And of course, these are not renewable fuel sources, so there will be fuel depletion, and many generations are supposed to live on this earth. So we have to, of course, conserve fuel materials for them as well. And as I mentioned in the previous slide, geopolitical equations are highly volatile, and they are also affecting, uh, in fact, the development of a country. So just like food security, energy security is also very much important for a developing country as well as a developed country. So the search of sustainable energy resources and technology is not just a problem for physicists, it's a problem, a challenging problem for engineers as well. So the main goals, obviously, are to have sources having low carbon power generation, and obviously high efficiency, affordability, of course, and renewability. Most importantly, the resources should not be depleted over a period of time. And one such technology that we are very much using is solar cell, simple photovoltaic cell. And we are using semiconductor material in this. The simple physics is like when, light from sun, it is an electromagnetic radiation, has certain amount of energy. The wavelength ranges from roughly 400 nanometer to 700, 800 nanometer. You could convert that into energy is equal to h nu. And when it falls on certain material, if the band gap is such that it will emit electrons, and if you could collect those electrons, that makes a current or voltage or whatever power, and that is basically exploited in solar cells, and that is a renewable energy source as long as sun exists, as long as the nuclear fusion process in sun continues and provide enough energy. So we have different materials, and we have, government of India is also promoting this, the Surya Ghar Yojana, Surya Ghar program with subsidy is actually to promote this kind of thing. So again, here we have the solar power. We are having this rooftop system, solar farms. Many farms are there actually in India. Also, there are so many privately and government owned farms are available. And so fundamentally, it's renewable, no greenhouse emission, no low maintenance, and we have subsidy scheme, PM Surya Ghar scheme available to us from the government. But engineering challenges in this case are the efficiency, basically the limited efficiency. So the semiconductor materials are basically used for this. In the beginning, we were using very much we were using silicon material, and the maximum efficiency it could offer us is about 20 to 25%. And so that is a challenge. Obviously, if you could make 100%, obviously you could have a better efficient system. And these are all intermittent. This solar energy or wind energy, these are all intermittent energy sources. It depends upon the season, it depends upon the climate. And I have a 5 kilowatt unit in my home, and during peak summer it gives me about 25 to 30 units of electricity, and during monsoon about 5 to 8 units, the same setup. And at night, and there is no energy at all, energy production at all. So it is highly intermittent, and obviously where there is humidity, of course, maintenance is also an issue from algal growth and all. So fungus and such growth. So engineering challenges, main engineering challenges is the limited efficiency, and obviously the storage of whatever energy we produce as well. And we have recently, there is a significant development in this, which one should probably take forward. These are called perovskite material, solar material. And in my university also, department also, one of the scientists and his team are actually working in this solar cells they are trying to make energy efficient solar cell. And these perovskite materials are basically new kind of material, and that is providing efficiency up to 30 to 33% or 35, maximum 33%. But we are confident or optimistic that we can have other materials, better materials for solar cell applications, and how to use it and how to have this is again an engineering challenge, and a lot of research is actually happening in identifying new materials. And another one important, even though this provide higher efficiency, one of the drawback of this perovskite material is that you see perovskite is CH3, NH3, PBI3. So it has lead, and lead is toxic. So in that way, it is the demerit of this material, but relatively better in terms of much better in terms of efficiency compared to the solar cells. I mean, compared to the silicon material. So renewable energy sources like wind and say solar cell, even though they are good, very less carbon emission, as I mentioned, they are highly intermittent. And another alternative option is nuclear energy. Now you know that right inside the atom you have the nucleus made of protons and neutrons, and you have lightest nucleus is that of hydrogen, which is simply a proton, and we have very heavy nuclei, and heavy nuclei are not stable. They do undergo some sort of decay, and one of the decay mode is fission, and which is nothing but splitting one heavy nucleus into generally two or more. It's also possible, two or more fragments, and that releases a lot of energy. Basically, E is equal to mc square. So from the mass differences, a lot of energy is released, and that is being used. The fission energy is used in nuclear reactors and nuclear bombs. Similarly, earlier I mentioned that solar cell and the solar technology will be there as long as sun is there, and as long as sun exists as the sun that we know. So in sun and other stars, this energy is released by the so-called process nuclear fusion, where lighter nucleus fuse and form a bigger nucleus, and again there is a mass difference, and that mass difference manifests in the form of energy. Again, using the same equation, E is equal to mc square, one could calculate that. So fission and fusion right inside the nucleus, the processes that are happening are basically wonderful reservoirs. Nuclear fission, you know that heavy nucleus splits into lighter nuclei because they are unstable because of the large presence of protons, which are positive entities. They repel each other, so there will be a huge Coulomb repulsion. So when fission happens, you know, uranium, for example, when it absorbs neutron, it splits into two nuclei and it releases some more neutron. So this neutron will be absorbed by another neutron. It again undergo fission, and so in that way, fission chain repeats, and this chain reaction could be a controlled one or uncontrolled one. If you could control it, that is what we are using for good purposes for the energy production in nuclear reactor. And if you don't control it, that is what you might have seen in the movie Oppenheimer. That is the technology behind nuclear bombs. So it's another source of, it's a great source of energy, and energy source which emits more or less zero, almost nil greenhouse emission, sort of clean energy. So if you look at the energy produced from these sources, in America, it's about 917.6 terawatt hour, which is about 20% of their total electricity. There are 94 nuclear reactors in USA, and France has about 57 reactors in that small country, and it is producing 64% of the energy. And if you look at the carbon emission, here it is shown. I have taken this from some article. So it is said that nuclear energy is not only reliable, it is also among the cleanest energy sources, with less than 1% of the coal emission. You see here a bar chart where nuclear energy is releasing about 6 metric tons per gigawatt hour. On the other hand, you could see wind energy is producing more, and even coal, one of the fossil fuels that we use in thermal power plants for electricity, it is producing 970 metric ton per gigawatt production. And you could see how clean nuclear energy sources are. So obviously there is an increasing demand for the clean energy and sustainable energy. And the only question is about the nuclear fuel. So another comparison you see, as I mentioned, this energy is stored in the nucleus, and 1 kilogram of, for example, if you use uranium-235 used as the fuel in nuclear reactors, we use 1 kilogram of pure uranium, because uranium appears in a few isotopes, and uranium-238 is about 99.2% approximately. Only 0.7% of the other isotope, uranium-235, is available to us naturally. And so if you have 1 kilogram of this pure 100% isotopically pure uranium-235, that 1 kilogram is equivalent to 3 million kilograms of high-grade coal. So just imagine, instead of 30 lakhs 3 million kilograms of high-grade coal, you need to use only 1 kilogram of pure uranium to produce the same amount of energy. And as I said, making 100% pure uranium-235 is not a silly job. That also costs a lot of investment and money. So generally, we go for enrichment, not as like 100%, maybe 3 to 5%. So you have natural uranium, which has got 7.7% of uranium-235. If you take 1 kilogram of natural uranium, that itself is equivalent to 14,000 kilograms of coal. And the greenhouse emission is relatively very less, and so it is one of the future energy sources or technology, at least for the next few tens of years or hundreds of years. So currently about 416 nuclear reactors are in operation. Roughly about 400 nuclear reactors are in operation around the world, and in India also we have a few, and which produce about 3% of the total electricity. So we have the fuel, uranium. We make that fuel. You can the fuel cycle is shown here, uranium ore, and then you enrich it, make uranium-235 more relatively, and then it is made in the form of pellet, and then you use it in the reactor core, and you'll insert it, and in chain reaction, to ensure chain reaction, the reactor will be maintained at critical condition. And when fission happens, neutrons will be the neutrons. When neutrons are absorbed, fission will be produced, huge amount of energy will be released, and that heat is used for making steam in the for making the steam, and with the help of the steam, turbines will be rotated, which will be producing the electricity. So here, just like a thermal power plant where you are using your coal or diesel or fossil fuel for generating steam, you are replacing it by a nuclear reactor where nuclear fuel through fission produces the sufficient energy, makes the steam, and then the rest of the process is the same. So that's how it works. And of course, there are many concerns as well. The moment I said nuclear reactor, many of you must have raised your eyebrows. So there are certain concerns and challenges as well. First thing is the reactor safety. The moment people mention about nuclear reactor and nuclear energy, people will be thinking how safe it is. And of course, there are reasons to doubt the safety. The Chernobyl disaster, Fukushima, 3 Mile Island, this happened. Of course, I admit that this happened. And main issue in this case is because of the core meltdown. So even to stop a reactor, generally we remove this. I mean, raise the fuel up. So that is called shutdown. Even after shutdown, you cannot completely stop the nuclear reaction, which will produce energy, which will produce heat. With that heat, even if the reactor is in the off condition, it can lead to damages. Core can be meltdown can happen. But today's reactors are very safe in terms of this. In the case of Fukushima, that happened because of earthquake and associated flood and all. Of course, if something like that happens, obviously there is a chance. So basically, the accident happened mainly because of the core meltdown. So the challenges before physicists, nuclear physicists, and engineers is to have better reactor material and the design, and it should also resist the radiation damage and high temperature and corrosion. That is one area. Another one is increased fuel burnup and to increase the efficiency and this interlocking systems, real-time monitoring. And if you could monitor the systems on real time, obviously, before the meltdown happens, before the accident happens, you could take remedial measures. And another most important say drawback of nuclear power is the storage and disposal of the waste, nuclear waste. When I say nuclear waste, this waste produced are radioactive material, and they are not so good for human or a living system. The radiation leads to mutation and cancer and death and other things. So and also some of these materials like plutonium, etc., if it goes to say bad guys, they could use it for bomb production as well. So in that way, it is challenging. Obviously, it is the waste management is, but there are strict protocols to handle this waste, nuclear waste, and dispose this nuclear waste. It's not a kid's game, in fact. And there are recently there are a few development advanced core material using chromium alloy and also chromium coated cladding, and then again iron, chromium, aluminum alloy, silicon carbide composites, and also when fission is produced, it produces a lot of energy, and then steam is produced, and then the system is actually in high temperature. There should be something which is actually cooling the system. So generally we use different coolants, liquid coolants, and now water coolants. And now there are technologies where liquid sodium is used, molten salt or liquid sodium is used, and then there are new generation still at a research level, but I am optimistic that within 10 years they will be commercialized, something called molten salt system, where this, for example, the reactor fuel itself is used as a coolant. So as I mentioned earlier, uranium-235 and 239 plutonium, these are used as the reactor fuel. Uranium-235 is only 0.7% of your total uranium, natural uranium. Plutonium-239 is synthetic. So you have generally one neutron is added to uranium and it becomes, through beta active decay, it becomes plutonium-239. In nature, it is available in trace amounts only. So even though nuclear power has a lot of merits, the fuel, the availability of fuel is a problem. Particularly when we try to have indigenous nuclear reactor and nuclear power, self-reliant things, then obviously you have to have the fuel source available to us. And here comes thorium-based reactors. We have world's largest thorium reserves, estimated about 1.07 million tons of thorium oxides. And a significant part of this thorium, about 2 by 5 or something like that, 1 by 3 or something like that, is in the coastal area of Kerala. So if you could use thorium reserves for generating power, obviously we can live we can produce power almost freely for next 400 to 500 years. According to estimates, these reserves are massive enough to support 500 gigawatt of electricity generation continuously for the next few hundred years, few centuries. But thorium as such does not undergo fission. Even if you collide it with neutron, it is not fissile or fertile material. So you have to convert it into fissile material, and that is where I mentioned you about molten salt reactor technology and breeder reactor technology. In breeder reactor, first we use this thorium, convert it into a fissile material, and in some of the molten salt reactors, you use both a mixture of thorium, uranium, and plutonium. So fission will be started from uranium or plutonium, and then at some point, this will be generating will be producing neutron plus thorium will make uranium 233, and that will be acting as a source of the fuel of the reactor. So this process will be continued, and we have sufficient amount, and the same source in the molten form can act as both the fuel as well as the coolant. That is the beauty of it in the case of molten source reactors. But as I mentioned, these are in the research level, mostly in the research level at the moment, and very soon we could expect to have them operational for energy production. So producing energy is one aspect where there are a lot of engineering possibilities, engineering challenges, physics challenges, and another one is battery and storing this energy. Of course, the world is battery powered, and we require energy technologies, and nowadays electric cars and electric vehicles are everywhere. We are using very much relying on lithium ion battery. As I earlier mentioned, renewable energy sources are intermittent. When the power is produced, you store it and utilize it when there is a less chance of power. So lithium is a concern in some sense. We are not very sure about how long it would go, but when it will be completely depleted, and it is volatile, low durability. There are so many problems associated with that. And another alternative, what research scientists suggested and engineers are very keen to, is sodium ion battery. And so lithium is not that lavishly available. We don't have those many lithium resources, but sodium is available. You can extract sodium from sodium chloride, the salt, simple salt. So there is a technology, sodium ion technology, battery technology, which is cheap. Sodium is very abundant, and a lot of research is actually happening to understand this, to develop these technologies. And then there are supercapacitors and flow batteries, where the electrolyte is actually separate from the conventional batteries. And a lot of work is actually happening in this area as well. And how much time I do have? Can I take 10-15 minutes? So another area I thought of, since I do work in nuclear physics, I thought I'll highlight this one also. The medical physics and healthcare technology also, a lot of engineering aspects are, developments are going on. We use radiation therapy for oncology. Previously, people were using chemotherapy. And then it is switched to radiation therapy, where X-rays or gamma rays have been used, and which will be used for killing, destroying the tumor cells. One problem in chemotherapy is that you are actually consuming that chemical. It will be affecting the entire body. In radiation, it is localized, but if a tumor cell is somewhere here, when you irradiate it, you are actually killing the tumor cell as well as a significant amount of good cells as well. So here comes another technology driven therapy, or therapy which is called a proton therapy. Here, you see that here on the left-hand side, there is a relative dose and depth from skin. So when these particles or radiation goes through materials, they will interact with the atoms or molecules. They will lose energy, and that's how the energy transfer happens. So gamma ray or X-ray has a lot of energy. When it passes through, it will kill it will transfer the energy, and that's how it kills the tumor cells in the case of radiation therapy. Now, the difficulty is it is killing all the other good cells also during its passage. So what about how am I going to localize this? Can I do that? So we can do it if we use protons. For example, you see here the energy loss when the particle is going with certain energy. In the case of electron, or in the case of X-rays, the energy loss on the right-hand side and the y-axis is basically the energy deposited in terms of dose. So the energy loss is predominantly distributed over a large distance. But in the case of proton, you see, initially it has got a very low energy loss, and then most of the energy transfer happen at some point, and then it stops somewhere. So that is what and this is called a Bragg peak, and that if you could utilize, probably you could save a lot of normal cells, and that is what is happening in proton therapy. Proton therapy is used based on this, simply by using a physics principle, the Bragg's curve, where a charged particle lose energy when they interact with the matter in a specific, in a localized area, completely can be utilized. So we have such proton beam therapy center in India. One is in say Chennai Apollo Cancer Center, and another one is in TMC. Proton therapy, I think this Tata TMC is India's first public sector proton therapy center. About 60% of the patient receives free treatments here. So, and here in Apollo Cancer Center and Tata Memorial TMC, Navi Mumbai, we have this proton therapy, and it costs significant compared to other countries. It costs much less here in compared to international standards. And you see, I have given a comparison here. In the USA, it costs about 1 to 1.5 crore, and here in India, it is maximum 10 to 30 lakhs per course, and that opens a lot of possibility for medical tourism also. And even TMC, about 60% of the treatment is for free for the poor people. And you see, again, I brought the same plot here, and X-ray energy loss is significantly large, spread over a lower distance. It can kill most of many tissues. Carbon, proton, it is better, but the spread is a little more. But you look at the green curve, the carbon ions. So the carbon ions lose their energy in a very short, very small interval, spatial distance. And this is the idea, the same idea is used in hadron therapy. Carbon ion beam is used, and highly precise, higher biological effectiveness, and fewer, if you have that kind of a sharpness, probably you could reduce the number of sessions as well. But unfortunately, so far, no centers in India for this hadron therapy. And interestingly, it is available in Japan, Europe, China, and even in Taiwan. I saw that there is one hadron therapy center. But the infrastructure requirement is actually high. As I said, we are using proton or carbon for cancer therapy. And you see, if you use proton therapy, you require a beam energy between 100 MeV to 250 MeV. This is very high velocity, actually. If you convert that energy into velocities, it will be around 1.5 into 10 to the power 8 meter per second. And our speed of light is 3 into 10 raised to 8 meter per second. So 1.5 lakh kilometer per second is the typical speed of approximate speed of this proton. And if you compare it with the designed speed of Vande Bharat, which is only 50 meter per second. So you need to achieve this kind of a speed, obviously you have to accelerate, and you need accelerators. And accelerators, if you look at the history, they were actually invented to see the smallest thing. To see a bacteria, probably you will use an optical microscope. To see atoms, use electron microscope. And if something is smaller than an atom, which is of the order of a femtometer, how would you see it? And here once again comes the beauty of quantum mechanics. Here we use the de Broglie wavelength. Lambda is h by p, and I have given one equation here. So if you have a proton of say 100 MeV energy, the wavelength is 12.4. If you have 1000 MeV, you can have the same proton wavelength is 1.24. Physics wise, to measure something, the least count of that instrument must be compared to smaller than the thing that you are going to measure. So by accelerating the particles, you could make them to probe a smaller thing. That is how accelerator actually originated. And so we have many generations of accelerators. So to generate, first you have to have particles, generated charged particles. And once you have charged particle, you place it between batteries. So there will be a force acting on it, Lorentz force, and then they will be accelerated. That is the basic principle. And so you have smaller accelerator and different kinds of accelerator. And if you see the generation of accelerators started with Cockcroft-Walton, and then you have these 1D graph generators, Pelletron accelerator. These are, the first two are linear accelerator. Another one is circular one, which is cyclotron, and then linear accelerator. So whether you want to go for why I'm mentioning this, in medical technology also you require accelerator, proton beams or carbon beams, and you have seen how effective it is for cancer treatment. So you can have a cyclotron, which is a circular accelerator, you can have a linear accelerator, and there are pros and cons. Linear accelerators, you need a lot of space, but less expensive. The circular accelerators are bigger. A circular accelerator requires bigger magnets, and that is very costly, very, very costly. And there are 30,000 plus accelerators in the world. And I am working in accelerator physics, nuclear physics, and for nuclear physics research, only 10% of the accelerators are actually being used. Remaining 90% are not used for research activities. So modern accelerator, you must have heard about Large Hadron Collider, very big accelerator, 27-kilometer circumference under the 170 meter beneath France-Switzerland border, and it's a collider. It is, why I just mentioned it, is a huge engineering marvel, actually. It's the largest particle collider machine in the world's largest cryogenic plant, world's largest refrigerator. The temperature is 1.2 Kelvin, liquid helium temperature. And physics-wise, we are actually trying to create the Big Bang. And anyway, I'm just making it fast, so not explaining much. It's the highest energy collider in the world and the largest cryogenic plant. I already mentioned that. And one of the reasons to set up such an accelerator is to understand how we are formed, the history of the universe. We believe that we started from a Big Bang, and only now we can create those we can go back in time and try to recreate that using high energy collisions, particle accelerator experiments. So the engineering challenges you see in this Large Hadron Collider, there is one detector called compact movement solenoid. This is one of the biggest magnet, which is producing a magnetic field of 4 Tesla magnet, and 1 lakh times stronger than the field of Earth. And it took about 20 years. And you see the size of this magnet. There are a lot of detectors all around. And see the people and see the high size. And inside this, it is one of the zone where reaction actually happens and produces a lot of particles. And this is a detector. It is looking at it. And engineering point of view, the design and construction of such a huge magnet is sort of great thing. And this is most expensive single device, world's largest solenoid. And this CMS itself will produce about 1 million DVD of data per year. So that is where data collection, data processing, and other things also coming into picture, and poses another challenge for the engineers. And generally, why you use this magnet? Magnet generally acts like a prism. Or it acts like a lens. So in beam optics, we use these magnets to bend the beam, focus the beam, and defocus the beam. And so when you deal with very high particles, heavy particles, high energy particles, obviously we'll be requiring larger fields and larger magnets, superconducting magnet. This is another big detector. So again, an engineering marvel. So this is, I think, the last slide. So more than 30,000 accelerators are operational across the world, and research field only 10%, medical field about 20%, and remaining 70% of the accelerators built are in the industry. So we were talking about novel materials, smart materials, quantum materials, etc. And these accelerators are basically used for producing such materials. Nano-destructive technique, for ion implantation, doping, which is very, very important in semiconductor industry, producing silicon wafers, etc., microchips and all. For this accelerator technology is highly used. And you see the engineering structure, engineering requirement, and engineering architecture in this sort of accelerators as well. So even though accelerator physics or the discovery of accelerator started to actually understand the fundamental physics problems, today 70% of these accelerators are used in industry, 20% is used in medical, and only 10% we people are actually using for sterilization. And in medical field also, I mentioned about cancer therapy, and then imaging and radioisotopes, and even medical equipment sterilization also accelerators are very. This is a non-destructive technique. Actually, it is used. And again, in army also, in the security forces also, for cargo security and authentication, smaller accelerators are used. So in accelerator physics, there is a huge opportunity for the engineering students and graduates in magnet development and beam optics, in many other fields, vacuum techniques, cryogenics. And these are those those areas where engineering students could excel, and for the future, vacuum engineering, RF and microwave generation. Most of these accelerators are actually providing pulse to beam, for which we require very high radio frequency signals. And microwave generation is also very important. And again, as I mentioned, data generation in these kind of experiments. Forget about the goal. It is up to us for physics people. Then when data is generated, it is an engineering challenge to store the data, where to store, and maybe a genuine event will be in one event will be in 1 terabyte, or that kind of a background. How to sort out the data, how to process the data, that is another engineering challenge. So, and heterogeneous data storage, all these things are future challenge. So it's one of the most important interdisciplinary and engineering intensive fields in 21st century. So I just mentioned about some websites where you could see we could teach quantum mechanics, and this is one University of Colorado. I just took a screenshot. I shared the screen. Probably I don't have it right now. So to teach photoelectric effect and see this double slit experiment, you could play with single particle to you can increase the screen brightness, you can increase the you can play with so many things here, and you see how actually the observables change in these simulations. And there is again simulations for particle in a box problem, tunneling problem. This is one case. You can play with the barrier, we can adjust its parameters, and these are wonderful for physics demonstration. Particularly when you teach quantum mechanics, it should not be simply teaching some differential equation and telling them to shut up and calculate. It should not be like that, I feel. So thank you so much. I think, yeah. So thank you very much. I don't know how effective this will be. If you have any questions, suggestions, comment, you are free to ask, or we can wind up the session otherwise. And if anybody wants this presentation, I can share, and probably you could get my email ID from the organizers. And there are a number of websites where some of this physics ideas could be beautifully taught to the engineering graduates. And again, for quantum sim, I mean, you can Google it nowadays. It is very easy. I also have a few resources where it can be done. Thank you. I'm done. Ma'am, say, ma'am.
Yes. Yes, sir. Thank you. On behalf of all participants, I sincerely thank you, Dr. E. Prasad, for the insightful and informative session. Thank you, sir, for
Thank
your
you so
time
much.
and support. Thank you, sir.
Thank you.
Thank you.